Uh, I'll let Dr. Frank introduce today's speaker.
Okay, right, thanks. So it is my pleasure to introduce my student Zhang. And Cong is a second-year PhD student in my lab. She got her bachelor degree from Nanjing University of Aeronautics and Astronautics, and then a master degree in industrial engineering in Penn State University. So she joined my lab like 1.5 years ago, and she's now working on traffic speed estimation and also driving behavior analysis. And she also has a lot of experience in the driving simulator studies. Okay, so today she will talk about her recent work regarding the vehicle trajectory reconstruction in a CAV environment. Okay, so stage is yours.
Thank you, Dr. Feng, and thanks for coming today. So today I'm very glad to share our recent work, vehicle trajectory reconstruction for freeway traffic considering lane-changing behaviors. So let's start. So vehicle trajectory is about the movement of the vehicle over time. It could provide us the critical information for various transportation applications. For example, the traffic safety, traffic efficiency, and the traffic environment. To improve the traffic safety, it could detect the traffic conflicts to avoid crashes and evaluate the safety performance and analysis drivers' behaviors like the illegal driving behavior. And to improve the traffic efficiency, it could help us to operate the signal timing and estimate the state like speed estimation and the planting estimation. Also, it could help to us to design the trajectory planning and improve the accuracy of the digital map. By using the vehicle trajectory data, it could help us to create the environmental friendly traffic environment, like it could reduce the fuel consumption and emissions. But we are still facing the problem like the missing trajectory data due to several reasons. The first is from the technical issues like different sensors, cameras, and the GPS devices may lead to the different coverage range, and this may us lose some trajectory data. From the environmental factors like different weather, stock lightings, different road conditions made us lose some trajectory data as well. So from the privacy concerns, somebody do not want others track their individual movement, identify their personal information from the data protection sides. And the data we collected may be the insufficient data because we may have the very low collection frequency and insufficient data quality with like the limited coverage. So that's why we need trajectory reconstruction to reconstruct the missing trajectory data into the more complete and continuous trajectory data. So let me introduce several methods for the trajectory data collection. So the most common and traditionally one is use the detectors or the infrastructures like the cameras. It could give us the very high spatial resolution data, but it also requires very high installation and maintenance cost. Also, the collect data may be the limited trajectory data. So the second popular method is using the connected vehicles. As we all know, they could communicate with each other and share the information like their speed, acceleration, their locations, and they also this data are also the time continuous data, but the sensors may be inaccurate and they require a very high penetration rate. So with the development of the connected and autonomous vehicle, they could provide us the more larger and wider perception sensors coverage, and also our collected data are the time continuous data, but it is vulnerable to the interference due to the occlusion problem. So in summary, we can see that the first one collected the stationary information, but the other two collected the moving information, which could provide us the more detailed information in a wider range of environment. So with the development of the over years, the researchers have developed many approaches and methodologies to reconstruct trajectories, and I list several main existing methods here. So first is from the traffic flow series side. So Chin 2021 reconstruct the trajectory for the intersections. They consider the hybrid approach integrating the Kalman filter with the variational theory. And Sun and his team 2013 reconstructed this trajectory using the mobile sensors. Also, the second very popular method is using the statistical modeling. When 2016, they used the maximum likelihood estimation based method to reconstruct the maximum likelihood trajectory of the prop vehicle by using the GPS updates, considering the travel time, the queue length, and the signal timing. So the last one is from the particle filter methods. In 2015, they consider this problem and they select the true trajectory from the most likely trajectory by using the Bayesian models. But this existing method still have some problems, like they consider the unobserved vehicles arrived uniformly, which is not really the truth in our reality. Also, they assume very perfect detect without any errors. This is too ideal compared to our real world. Another important point is they do not consider any lane change behaviors in their study. So as we all know, the changed lane behavior is very common driving behavior, and it is unreasonable if we just ignore it. It not only influences the macroscopic level, but also the macroscopic traffic systems. So we need to consider the lane change behaviors. So let me introduce our objective. So we need to reconstruct the trajectories considering the lane changing behaviors and the occlusion in the Freeway environment. So let's see this example. This is a schematic of our current problem. This is the 6-lane highway, and there are several CVs here. I marked as blue color, and each CVs will have the certain range, detection range. I marked as the blue circle. So within this detection range, the detected regular vehicle are marked as green color, but there are still some undetected regular vehicle due to the occlusion. So outside this detection range, the regular vehicle are undetected regular vehicle. So in another word, our job is by using the trajectory of the blue vehicle and the trajectory of the green vehicle to reconstruct the trajectory of the yellow vehicle. So here is a schematic of the CV detection algorithm. So we consider the CV site travels in a straight lane, and if at least one of the 4 corners of the vehicles could be detected by the CV, then we assume that this vehicle is a detected regular vehicle. Otherwise, this is undetected regular vehicle. So here is the time-space diagram of the particle detected trajectory between the pair of CVs. So x-axis is the time and y-axis is the distance. And there are 2 loop detectors equipped at the beginning of the road segment and the end of the road segment. So there are 2 CVs, and the trajectories are marked as the red color. So in the middle of these 2 CVs trajectories, we can find there's a lot of black trajectories, and these trajectories have some missing parts. So the first missing part is area 1. This is within CV's detection range. That means this area's trajectory occluded by the other vehicles. And area 2 is the area outside the CV detection range. So our job is to reconstruct these 2 areas trajectory. So to the end, we need to make some major assumptions in our project. The first is, if the observed car following behaviors are significantly different with our expected behaviors, then we assume that there might be undetected lane change vehicles between a pair of drives and CVs. So in this case, that means if the vehicle I changed lane from the current lane to the target lane, then the following vehicle B in the current lane will accelerate due to the larger gap, and the following vehicle of the target lane, vehicle A, will decelerate due to the caught-in behavior. The second assumption we made is the entering and the terminal vehicles information in each lane are collected by the infrastructure sensors. So the cameras installed here are collected the vehicle's paint information, and the loop detector we collect here to collect the vehicle's speed, acceleration, this kind of information. So let's go to our methodology. So first, we need to input our incomplete trajectory data in, and then we need to predict the lane change algorithm. First, we apply the Pettit test, and then we utilize the rule-based optimization algorithm. So after this step 2, we will determine if there existed lane change behavior. So what is the optimal lane change time point, and which vehicle changed lane from which lane to which lane. So after that, we will apply the car following models, and there are 2 car following models applied here. First is intelligent driver model, and the second is NGSIM car following model. So after all this step down, and then we could reconstruct trajectories. So let's go to the Pettit test and see how this works in our project. So the Pettit test is a non-parameter test. It could find the sudden change of the continuous time series data. So the trajectory data is the time continuous data. So we could apply this Pettit test into our problem. So our objective is to find the sudden change of the acceleration of the following vehicles A and B to estimate the lane change time points of the ego vehicle, vehicle I. So we consider 2 continuous probability distribution F1 and F2, and there are 2 hypotheses. The first, they are same with each other, and second, they have the significant difference with each other. So our goal is to find the most significant change time point tau at the location KT. So we use the P less or equals to 0.5 to 0.05 to reject the non-hypothesis. So after the Pettit test, we will have 1 or more lane change time points. So to make sure the accuracy of our Pettit test, we apply Pettit test every 5 seconds. So after that, we will have 1 or more multiple lane change time points. Now, if we have 1, so that's it. But what if we have multiple lane change time points? So that's why we will apply the rule-based optimization algorithm here. So I separated them into 2 different cases. The first case is without interference. So in this example, that means there's only 1 vehicle change lane from the lane 1 to lane 2. And our objective is to minimum the total distance error between the expected trajectory of the surrounding vehicles AB and their observed trajectory of the same surrounding vehicles. The second case is with interference. That means in this case, vehicle I changed lane from lane 1 to lane 2, and the vehicle J changed lane from lane 2 to lane 1, and they have the overlapping lane change time intervals. So we need to consider this as a group to minimum the total error between the expected trajectory of the surrounding vehicle AB and their observed trajectory of the same vehicles. After that, we need to reconstruct the trajectory, but we still need the apply the car following models. The first we use is IDM car following model. It considers the car following speed, maximum allowed acceleration, desired time headway, comfortable braking and deceleration, leading vehicles speed and safety distance. So the second car-forming model we applied here, mentioned by you 2008. So this car-forming model calibrates by using the NGSIM data set. So we reference it as the NGSIM car-forming model here. So it considers the upper bound driving distance and the lower bound driving distance together. So in the upper bound driving distance, it considers the car-forming rules, acceleration ability, maximum desired speed, maximum safety distance. And in the lower bound driving distance, they considered the deceleration capability and the current position to avoid moving backward. After that, we did a case study. So this is the area we used in our project. So this is the NGSIM US101 data set, and the study length is around 160 meters. So on ramp with 6 lanes. So the experiment design, for experiment design, the CV's detection range is from the 80 meters or 90 meters to 100 meters. And we have a very low penetration rate of the CVs, it's around 2.7%, which covers the 253 lane change cases. So before we use the NGSIM US101 data set, we need to smooth this trajectory by using the Kalman filter. So let's see the prediction results. Overall, the prediction result is pretty good. So 253 lane change time points are estimated very accurately with the average error of 0.63 seconds. So let's see this table. This is the comparison table between the accurate lane change time points with the predicted lane change time points. So the first column is the vehicle ID, and the second column is the candidate time after the Pettit test. As you can see, they have the multiple lane change time points. But after we applied the rule-based optimization algorithm, they only left one optimal lane change time point. Then we compared with the actual lane change time points, and we can find the difference between them. So most of them are 0 or 1. Only 2 of them are 3 seconds. So overall, the prediction results are pretty good. So after that, I will introduce this plot. This is the reconstruction trajectory by using the IDM car-forming model with 6 lanes. So the real trajectory marked as the green color, and the predicted trajectory are marked in red color. And the blue dots are the detected trajectory. So as you can see, due to the IDM considers the following vehicle's behavior will influenced by the leading vehicle's behavior. So there might be the accumulated error here. But let's see the NGSIM car-forming models results. They do not have these issues because this data set fits the NGSIM data set much better. This model fits NGSIM data set much better. Yeah. So let's go to the performance evaluation. So we separate all the vehicles and the lane change vehicles separately by using the different car-forming models with different detector range. And the MAE here, the maximum MAE is less than 4 meters. And with the increase of the detection range, we could find that the percentage of the reconstruction will reduce. So our contribution could be summarized as following. The first, it is the novel trajectory reconstruction method for the freeway traffic considering lane changing behaviors. Second, the lane change point estimation method is proposed in a very high accuracy. First, we applied the Pettit test, and then we applied the rule-based optimization algorithm. The third point is we implement a very low penetration rate, is around 2.7% of the CVs with MAE of less than 4 meters. So I think that's all for my this presentation, and I'm open to any questions. Yeah.
What did you do with these results?
What
is the motivation? How you use the information?
Mm-hmm.
For what purpose?
So you mean the vehicle's trajectory reconstructions purpose?
Okay. What
So,
did you do with it?
Okay. Let's go to the first page. So when we use the vehicle trajectory data, it could used in different different areas to improve the traffic safety. We could use this trajectory to reconstruct to detect the conflict to avoid crashes.
Yeah, I understand that. But how would you how would you use it? Is it for automated situation, or is it for mixed traffic?
It's mixed traffic. Yeah, because
if it is an automated situation, you can play God. You can decide that how I'm going to separate them for safety. Do you understand what I'm saying?
Yes.
So it's a mixed traffic. I want to know what I'm going to do with it, this information. Who will use? Individual vehicles will use this thing?
Oh, I see your point. The vehicle could use this thing, and the researchers could use it to.
No. The researcher is creating information to implement, to do something, right? I don't know what I'm going to do with it. How would you use it in real world, in practical sense?
Okay, so we use this after we collected the trajectory data. Otherwise, we cannot reconstruct it by using all of observed. Yes. So in this mixed traffic, so as we can see, the CV's penetration rate is really low. So in this current stage, we the CV's in our real world, the CV's penetration rate is very low actually. So it's very useful to apply this algorithm into our reality to reconstruct this kind of information and use this continuous complete trajectory information into the next stage research. Yeah.
We are not talking. You're talking about research. I'm talking about.
I mean, I'll give you an example. Is that, for example, for adaptive traffic signal control, right? We need to estimate, for example, the queue length. We need to estimate the mean delay. But with this partial information, what we get is also partial. So with the reconstructed traffic state or the trajectory, we can better estimate the performance, and this as an input to the traffic control models, for example. Traffic signal control models.
So traffic control will make sure the vehicles use this separation, or that is the headways or whatever keeps them, right? The headway between vehicles.
It really depends on the resolution of your downstream application, right? As an example, I gave you like traffic control, then probably we'll only need aggregated information like delay, total delay, or total queue length. But if we achieve this example for example, for the vehicle trajectory planning, then we really need to know the detailed trajectory of all the surrounding vehicles. So that's why we need the detailed trajectory.
I don't understand, but then other people ask questions. Who is going to do the trajectory planning for what? So traffic control center will do the planning. That means planning means what? Keep them vehicles separated, the headways. Is that right? What is the trajectory planning in a traffic, in the real world, the continuous traffic stream?
So this is mainly for the autonomous vehicle design. Autonomous vehicle design.
Autonomous vehicles?
Trajectory plan.
Okay, so in an autonomous situation, I don't need all this. I can decide how I'm going to, for safety, that the following vehicles does not go hit the leading vehicle, I can keep it separate based on the speed of the following vehicle and the leading vehicle. Is that right? So if I do that, I can put that thing in the algorithm that how I'll keep them separated. Also, when I'm changing lane, I'll make sure the guy who is behind me, if I know his speed, I can keep the headway, safe headway. So think about, it's good for research, but how to implement this thing, give some thought.
Okay.
Yeah.
Sure.
Okay.
Thank you for your
That's how I
suggestions.
other people.
Thank you. Frank?
So I got a question. So could you please go to the next objective slide? Construct all the trajectory for all the vehicles, or it's just the neighbors of the green vehicles?
All of the vehicles. As you can see in the results section, we construct all the linked vehicles. Here.
Yeah. So how did you do that? So generally, when it's the immediate, like the neighbor of the green vehicles, I can understand because they are affecting each other, right? They're affecting the green. But what about like the second neighbor? How to do this?
Yeah, because let me go back to the methodology here.
Yes.
So in this step 2, we apply the Pettit test and the role-based optimization. There two are lane independently algorithm. So for each lane, we will apply these two algorithm.
Yeah, I understand because like your assumption is that when you cut in, you will affect the later vehicles, and if you leave this lane, and then the following vehicle will accelerate. Right? This is the basic assumption. Right?
Yes.
So in your previous figure, could you please go?
So
if this yellow car makes a lane change, how will the yellow car on the upper lane will be affected?
What do you mean by upper lane? Is here or here?
The upper two lanes, right?
The upper two lane will consider as a group. This two lane will consider as a group. So so on and so forth. We could get the 6 lanes.
So how about the vehicle in the right middle, right? Like right. the one before your the left change one.
The right middle is where? Right.
In the middle.
On the middle. Okay.
I think I should come back.
Okay.
Yeah, exactly. For example, this vehicle.
What that vehicle has to do with the changing lane?
So how do you detect the trajectory of that vehicle?
So this vehicle, if this vehicle's leading vehicle have the lane change behavior, then we could apply this kind of algorithm to predict this vehicle's behavior. Otherwise, we do not consider there's any lane change behavior.
Okay.
It's called, yes, in a very congestion driving environment. So they will influence each other's driving behavior.
So like another question is that how do you differentiate between is a random a speed down or being impacted by another lane changing vehicle?
We use the Pettit test to find the sudden change of the acceleration.
So actually, this is a question towards your assumption. So how do you differentiate between I just randomly press the brake pedal or I was intervened by some cutting vehicle? How to kind of resolve this kind of conflict? Yeah, if I just randomly press a brake pedal and then I decelerate rate, and then maybe in your case you are detected as a.
Oh, you mean there's no lane change?
Yeah, but I just randomly press the pedal.
You're overspeeding, you realize it.
Yes, exactly. Yeah, that's what I thought. Yeah.
This is interesting point, but in our case, at least in the limited study length, we do not fit into this problem because this is very congestion road segment, and if your behavior is not expected, it will lead to crash.
So generally, this can be applied into this kind of dense environments, right? So
Yes.
you cannot make random lane changes, or you cannot accelerate or decelerate like randomly. You have to follow some rational
Rows,
rules.
yes.
You know, if it is a near congestion traffic,
Mm.
I would argue that you cannot, a following vehicle cannot just adopt or look into the leading vehicle, only the front, the leading vehicle. I would suggest that perhaps
Mm.
two leading vehicles, the leading vehicle's
Two
leader,
leading wheel.
two.
Okay.
And because when you're near congestion,
Mhm.
you will assume or you will sort of think about what the leading vehicle is doing, but the leading vehicle also doing the same thing, and it will come back to that. So I think that two vehicles in front of you,
Mm.
a tissue paper, is old RGB paper, that then you can backtrack and make computations.
Yes.
Near congested situation, that will be that has to be considered.
Right.
Yes.
This is actually exactly what why this can only be applied to medium or
High
near
volume.
congestion situation where the vehicles are interacting with each other.
Mhm.
If it's free flow, then
Yeah,
We need to
yeah, we
extend
cannot
our
observe
algorithm.
that then.
yeah, that's it. Yeah.
Thank you,
So
Doctor.
these things are coming back, not following.
Yeah.
Yes. Yes. Yeah, yours first.
I'll just say, I got a few questions
Uh-huh.
regarding your experiment.
Okay.
Actually. First of all, you're comparing your proposed method with pure IBM, right?
So
Your
need I
experiment
go
had
to the this one?
methods with, no, experiment.
Okay.
Yeah, you're comparing your method with IBM, like the IBM models. However, you're considering lane change, interpreting consideration of lane change, which are missing from IBM. I was thinking, like, why not compare your methods with other methodologies, such as, for example, in Sumo, they incorporate both IDM along with other like lane change out in 2013 or something like 2015, the lane change models. How would you compare these two methods in the experiment to show that by incorporating this kind of lane change assumptions will make your prediction better than those two?
Yeah, I understand your point. That's very good point. So due to the limited time, we do not compare our algorithm with the other algorithm. But I think maybe later we will add this to our future research, so that will be better. Yeah.
Yes. And another point is about common filter to the data sets. I know that common filter is a very common adopted way to smooth trajectories. I was wondering how common filter contributes to your final accuracy. You know,
What?
You smooth your trajectory
You
with common filter. Right?
Oh, Kalman filter.
With
Uh-huh.
common filter.
Uh-huh.
It can somehow induce measurement errors. The measurement errors conform to that Gaussian assumptions in that common filter. I mean, if it's not a raw data, you're using common filter to smooth your trajectories and compare your predictions to that smooth trajectories. I was wondering if the common filter contributes to something accuracy in your final results.
No, I don't think that Kalman filter work. Here I mentioned Kalman filter will smooth our trajectory. That means it will drop the noises which equipped by the other equipment, but will not just drop or delete the information of the sudden change of the acceleration, deceleration, this information. It's a very common method we need if we want to implement the data set. First thing is we need to use like the Kalman filter, this kind of filter to smooth it. So this is very common. Yeah.
I'm a little bit curious about this common filter. What are the two sources of input for the common filter? Like, what is the state estimation and what is the sensor? Yeah, I'm a little bit curious.
How to the base model of common filter inputs. And
Yeah, what are the inputs of this common filter?
That is the NGSIM raw dataset. So we download the dataset online, yeah, and after the Kalman filter, so we use the smooth trajectory after this filter.
Okay, so
yeah.
this is the booting function in using, right?
Mhm.
Okay, let me certify.
Yeah.
Thank you.
I think it was slide 12 or 13 in which you have like these are 12. In the interference scenario, wouldn't A and B both still have a car in front of them and they wouldn't brake at all since the gap will stay the same? So will you miss both of those lane changes? Is that what you mean?
You mean the first one or the
With
second?
interference, the second.
With here? So you mean the crash things or?
No, so if I and J are both changing the lanes, then A and B won't need to like fix their gaps because they still have a car in front of them.
Mhm.
So are you missing those lane changes? Like, is that what you mean by this slide?
Okay, I can explain again. So with interference, that means if they have the overlap lane change time intervals and they have the vehicle I change lane from the current lane to the target lane, in the meantime, not in the meantime, in the overlapping lane change intervals, there's another vehicle change from the target lane of the vehicle I and go to their current lane. So they will we need to consider them as a group to consider the minimum distance error between these group vehicles.
So how would you identify that lane change? Because A and B still have a car in front of them, they're not accelerating or decelerating.
But as I mentioned here, they are not conducted. Yes, they are not conducted at the same time. So the vehicle A and B will have the 2 second change, at least 2 second change time point. Yeah. So that's why we could figure out this problem. Mm.
So that's why you're grouping the lanes. So for the 6 lanes, you have like multiple groups to find those interferences.
Mm-hmm. Mm-hmm.
I just want to ask that I noticed that you used two colorful models. One is IDM, one is based adjusted by NGSIM data, right?
Yeah.
But your testing is also on the NGSIM data.
What do you mean by test on the NGSIM data?
The experimental data.
Yes. That's why we want to use this NGSIM conforming model here.
And now my question is how to prove the generalizability of your proposed method. It works fine under the NGSIM data, but does that means that if they apply to other scenarios, like other new congestion scenarios, the car-following model can still have such a good performance?
That's why we need to calibrate the car-following model at first.
Okay.
So before I apply the car-following model, the parameters I used first I need to calibrate it, and then I use that set of parameter to apply to our this project.
So basically, you assume that you can have the historical data to calibrate your model first.
Yeah.
Okay.
I have one question about the problem definition. Can you go back to slide 10? The blue vehicle knows the location of the green vehicles, and then they want to predict the trajectory of the yellow vehicle. And this is your problem. My question is that your problem knows the number of yellow vehicles in advance.
No. We do not know how many undetected regular vehicles surrounding.
So your algorithm need to predict how many vehicles in the system or not?
We have a loop detector as an end.
Yes, we have the loop detector at the beginning of the roadside and the end of the roadside. Also, we have the camera here. The camera collects the vehicle's plant information, so we know the vehicle's sequence when they go into this road segment, and the road detectors collected the speed and like the acceleration information. Because the road detector have already equipped it here, so we know the location information. Does that answer your question?
So that you know the total number of vehicle.
Yes, we know
So
the
you cannot-
if they yes. Any other questions?
Can you go back to slide 2? I'm looking at these applications, and it looks like your study specifically talks about freeway segments which are near congestion, and that require lane change behaviors. So you would not do that for fuel efficiency or emission analysis because you don't need the lane change behaviors.
Yes.
Similarly, you don't the intersections don't apply. So the only 2-3 things that I think are applicable here are driver behavior analysis, trajectory planning, and digital map accuracy.
Traffic.
For the driver behavior analysis, I'm wondering, is this a good idea to do this because you are using a model to make assumptions about driver behaviors, to make analysis about driver behavior?
Yeah.
So it could run into a circular loop. Like you're making some assumptions how drivers behave, then you're constructing the trajectories, and then you're assessing how drivers are behaving. So there's some.
Yes. So here I listed here because it's just like the illegal. If there's a legal behavior, so we could by using this reconstructed trajectory to analysis drivers' behavior. If they avoid the rules, if they follow the rules, so we could use this kind of reconstructed trajectory information to analysis this behavior.
Okay. Okay. And do you need that for digital map accuracy as well?
Not yet, but I think that's a good idea to look deep into it.
Okay. And also on slide 12, this is the last slide that you mentioned. Why do you need both the cameras and the loop detectors on both the sides?
Yes. Because we need to know the number of the vehicles they come into our road segment. This is the first thing. The second thing is we need to know the sequence of them. Because if they change the lane or if there's the overtaking behavior, they may have the different sequence compared to the initial sequence.
But how do you do that? Because do you track the vehicle ID, each vehicle's ID?
So that's why the camera installed here, so they can track, collect the vehicle's ID at the beginning and the end, so we can.
That's pretty interesting because so they would do some image processing or do they do plate detection? Like how do they identify that this yellow vehicle when it exits the road segment, it's exiting on lane 2 or 3?
So at the beginning of the road and end of road, we know that information, but within this road segment, we do not know.
Plate recognition.
Yes, the plate. Yes, the
plate
plate.
not need the detector.
Yes.
If only install camera, it will do. Okay.
And can the camera detect all the lanes, the number of vehicles on the lane?
Yes.
I think maintain in an automated situation is all the vehicles are automated. Okay? Driver doesn't matter. It's a vehicle. So the acceleration and deceleration capabilities of the vehicle, those are important. But what does the driver have to do? Without driver, the vehicle can go, right? You don't need a driver. It's a vehicle. So vehicle characteristics or vehicle performance becomes important. That deceleration model and acceleration model. All the control will make sure that you keep safe distance depending on the speed of the relative speed. So keep some thought about that. Okay, very
Thank
good.
you,
Anybody any other questions?
Yeah, you have.
So I have 2 questions.
Uh-huh.
Could you clarify the role of CCTV in your study? So just for data collections or for other things?
Oh, it's for first we need to reduce the penetration rate of the moving vehicles, prop vehicles. As you can see, if we use the CVs here, we require the very high penetration rate. So that is the first reason. The second reason is it could collect the surrounding vehicles information, and also they could share the information between the two CVs in this figure. They could share different information and they could observe the surrounding vehicles information.
So actually, the primary role of the CAV is a reconstruction, right?
Yeah. Yes. Yes.
My second question is about the lane change algorithm. So does your algorithm predict based on just the changes in the acceleration rate, right?
It's like the starting point of the acceleration. The acceleration could be considered as a continuous time series data. So we use this Pettit test to would find the sudden change point of this continuous continuous data. Yes.
However, in your study, actually NGSIM data, the time period is the congested time period, right?
So you mean here?
No. So go to experiment. Your time period is the AM period, right?
Let's go to 6.
So can you clarify which slides or which scenario?
Okay. So it's about the description of the NGSIM data set.
Oh, later.
Yeah. So
Okay.
so the time period is the AM period, right? So 7:50 AM to 8.
Oh, yes.
AM peak.
Yes, AM.
So in the case of the traffic situation really would be congested, right?
Yes, it's
So
congested.
because I think that there are so many the noise in acceleration rate.
Oh, that's why we applied the Kalman filter to smooth it. We want to reduce the noise.
Yeah, so my question is, how many vehicles decide based on their rate changes based on the acceleration rate changes? Because if there is no the available rooms on target lane, in that case the vehicles cannot lane change, right?
Yes,
So
if there's no
how can you
room.
detect these the situations about the target lane available slot?
Okay, so I think that's a very good question. So first, we do not like statistically check if there's any enough road to lane change. We just check if there the existence of the lane change behavior. So if it existed, what is the best solution of the lane change time point? If it's not, then the following vehicle's behavior will be the same as before. Yeah.
So based on your algorithm, how many lane changes are as predicted in your algorithm? So you cover the 250.
Yes.
So how many lane changes are predicted in your case?
All of them are predicted. Yeah.
There is no any overestimations.
So this difference could show that all of them are predicted, and here I only listed after the Pettit test we have the multiple lane change time points, but most of them.
I think the question is whether some lane changing are missed in your prediction,
Yeah.
or something you predicted here are not the real lane changes in the data set.
Okay,
So you predicted the covered lane changes, right? However, in your algorithm, there is any overestimation. That means that the vehicle is not lane changing behavior. However, in your algorithm, say there is.
I do not think that that's included in this experiment.
It's a good point. You need to check that.
I checked before.
So all the lane changes are
yes, are correct.
Okay.
Yes, thank you.
Yeah, it's okay. Any other
All right.
questions?
Yeah, it's time. Okay, very good.
Thank you.